This video is going to give you some background as to where the annuity formulae come from. Before we can look directly at the formulae, we need to have a look at what a geometric sequence is. So if we have a look at the sequence 3, 9, 27, 81, you should be able to see that you multiply by 3 each time to get the next term, and so on. That is a geometric sequence. And by definition, a geometric sequence is any sequence with a common ratio. And we call that common ratio R. Now, in this particular sequence, our common ratio is 3, because we multiply by 3 every time to get the next term. But now let's see a general formula for our geometric sequence. In other words, a general formula for Tn. Let's see how we get that. Right, so let's look at our first term, and if you remember studying sequences in grade 10 and grade 11, you will know that the first term we use an A to represent. So we know that the first term, T1, is A. Now I've already told you that the common ratio is R, and that we need to multiply by R to get the next term, which would mean that the second term, T2, is A times R. Okay, cool. Let's look at our third term. Again, to get our third term, we need to multiply by our common ratio R. So that's AR, and if we multiply that by R, so let's do that, AR, we multiply that by R, we get AR squared. Let's have a look at our fourth term and see if we can start to pick up a pattern. Our third term was AR squared. We had to multiply it by R, so we're going to get AR cubed. Can you see the pattern yet? Take a moment to think about it. Okay, so we take our fourth term, AR cubed, we times it by R, and we get AR to the power of 4. Let's fast forward a little bit to, I don't know, say T100. You should notice that in the fifth term we had a 4, in the fourth term we had the exponent 3, in the third term we had the exponent 2. So yeah, I'm sure you've guessed it by now. T100 would be AR to the power of 99. But obviously we want to generalize that. We want to get our formula, our nth term. So let's try for Tn. Now we know that the exponent is 1 less than our n, so we're going to have A R to the n minus 1. Now that is our formula for the nth term of a geometric sequence. So you could use that to find the nth term of any geometric sequence. Now let's take that one step further. When we add the terms of a sequence, so we add them together, we get what is called a series. And we represent our series by Sn. So instead of Tn for the term, our series, which is the sum, is Sn. Now we need a general formula for a geometric series. In other words, a general formula for adding up all the terms in a sequence. Because it's quite easy if there are 4 or 5 terms, maybe if there's 10 or 11 terms. But what if you're adding up 1,000 terms or, 5,000 terms? You don't want to do that manually. That'll take you forever. So you need a formula. So let's have a look at what a geometric series looks like and develop that formula. So would you agree that I can write out a series of geometric terms? Remember, we use an Sn. So I've got my Sn, my first term is A. I add my second term, which we know is AR. Then my third term we know is AR squared. Now I can keep on going. I'm not going to write them all out, dot, 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 to show you that I'm keeping on going. Now my second last term in a sequence would be ARn minus 2. If that doesn't make sense, let's just have a look at the last term, the general term, ARN minus 1, which we saw in the previous description of a geometric sequence. If AR to the n minus 1 is the last term, subtract 1 from the n minus 1, and we're going to get n minus 2. That's how we get our second last term. Now there's a little trick in the proof of this general formula. Now the little trick is to times everything in that equation I've just written by r. So I'm going to times everything by r. You might be thinking, how do I know to do that? Don't stress, it's actually a little trick in the proof. So let's have a look. If I times Sn by r, I'm going to get Rsn. Now, if I multiply A, that first term, by R, I'm going to get AR. And I'm not going to put it directly below, I'm actually going to put it under the other AR. You'll see why just now. Now if I go to the second term, AR, and I multiply it by R, I'm going to get AR squared. So I'm going to put that there. Trying to line all terms that are the same up. Okay, now actually there's another term before this one, which is ARN minus 3. If I times ARN minus 3 times by R, I'm going to get ARN minus 2. And if you've forgotten some of your exponent laws, just bear with me, let me quickly show you how that worked. So here, if I had ARN minus 3, and I multiplied it by r. Remember, when you multiply powers, you add the exponents, so it's r to the power of 1, which then becomes ARN minus 3 plus 1, which is ARN minus 2. That's how I got that right there. Okay, cool. Just take that all out. Okay. Similarly, if I get ARN minus 2 and I times it by r, I'm going to get ARN minus 1. And then, if I take my last one, ARN minus 1, and I times it by r, remember I'm adding the exponents, so I land up with AR to the power of n. Okay, so now what I'm going to do, let me just pop a line under here. Now what I'm going to do is I'm going to subtract this second line. So I'm going to put this one first and subtract the first one from the second one. Now it's totally legit mathematically to do that. And again, it's a little trick in our proof to get our formula. So what I've got here is Rsn, and I subtract Sn. When I subtract two equations, I'm going to subtract everything that's in line. So here, that's my Rsn minus Sn. Here I've got 0 and I subtract a, which gives me negative a. Here I've got AR and I subtract AR, which gives me 0. Here I've got AR squared, I subtract AR squared, which gives me again 0, and I can carry on. You'll see that every single underlying term gives me 0. Except when I get right to the end, AR to the power of n minus 0 is AR to the power of n. Right, so now let's simplify that a little bit. If I look at the left-hand side, I can take out Sn as a common factor, in which case I get Sn r minus 1. And here I have negative a plus AR to the n, which I can rearrange and write as AR to the n minus a. Cool. Now remember what we're aiming for. We're aiming for a formula for Sn. So what we actually need here is our Sn on its own. So we need to divide both sides by r minus 1. In which case I get Sn is equal to, now I've got this on the top, which you can actually see straight away you can take out a common a, so I'm going to do that in this step. and I've got r to the n minus 1. And remember, we are dividing by r minus 1. Now this is our formula for Sn, the sum of a geometric sequence. In other words, this is the formula for a geometric series. And this is the formula that we're going to draw on when we're looking at the formula for an annuity. Okay. All right, so that's the formula for a geometric series. Let's dive straight into the link between a geometric series and our annuities. Now I'm going to look in more detail later at what an annuity actually is. But for the moment, an annuity is a series of equal payments at regular intervals subject to a rate of interest. And the first one we're going to look at is a future value annuity. Now, in a future value annuity, money is invested at regular intervals. So you're investing money, putting it into stocks or into a savings account, and you save money for the future. That's very important. First, I'm going to start with an example because it might be easier to see. Then we'll generalize it and look at a formula for future value annuities. So let's start with this example. Suppose that 1,000 Rand is invested every month, starting 1 month from now. That's important, but in a later video we'll discuss what's so important about starting straight away or 1 month from now, etc. For a period of 10 months. Interest is 18% per annum compounded monthly. Now, the future value of an investment after 10 months would be the sum. So we're looking at the future value would be the sum. Now, that's quite an important word. Now that you know sum links to series of all the payments together with the interest that they earn. As with any finance question, let's go straight to a timeline to picture what this looks like. Okay, so here's my timeline. I know that we've got a total of 10 months, so let's just pop the line in there. See if I can get these roughly equal. So here I've got T0, T1, T2, T3, T4, T5, T6, T7, T8, T9, and T10. Okay, it goes a little bit over, so actually I'm just going to shorten my line a little bit. Take that out. Okay, great. Now remember, we're aiming for a future value, so I'm just going to put an F there. We use an F to represent future value and a P, you'll see later, to represent present value. Now what happens along the way is I pop in my 1,000 Rand every month, and that happens 1 month from now. So I know that I'm going to be putting in 1,000, 1,000, 1,000, all the way up to T10. Okay. Right, and let's just have a look at what our interest rate is. I'm just going to pop it underneath. It doesn't change. Our interest rate is 18%, and remember that it's compounded monthly. Cool. So let's have a look what that looks like. Now, each of these 1,000 Rands needs to make its way all the way to the end. Now, for the purpose of visualizing this as a geometric series, you'll see later, I'm going to start with that 1,000 Rand and work my way back. So, I want to find what my future value is. And we're working with compound interest. So I want to find my future value. Let's start with this 1,000 Rand here. This 1,000 Rand is already all the way at the end, so it doesn't accumulate any interest. So I've got that 1,000. Now I add, let's look at this 1,000 here. That one accumulates interest for 1 month. So I'm adding 1,000 and its interest, so 1 plus 0,18, 12, just for 1 month. Let's look at the next one. That 1,000 accumulates interest for 2 months. So I've got 1,000 and its interest for 2 months. Now I keep on going, I look at each and every one of those till I get all the way back to this 1,000, and it accumulates interest for 1, 2, 3, 4, 5, 6, 7, 8, 9 months. So that 1,000 Rand accumulates interest for a total of 9 months. Great. Now, you might have already seen that this is, in fact, a geometric series. Now, remember our formula for geometric series, let's just pop it over here, is Sn equals a r to the n minus 1 over r minus 1. So we need to remember that. Okay. Now, in this case, in this geometric series, our a is 1,000, that's our first term. Now have a look at what you're multiplying by each time. You're multiplying by what's in the brackets. Our 1 plus 0,18 over 12. That's our r. That's what you're multiplying by to get each successive term. And in this case, how many terms are there? There are 10 terms. You might see a 9 here, but remember the first term is this guy over there, that 1,000. So let's plug all of these into that formula for geometric series. Now instead of Sn, we're going to use an F for future value. Okay, so in this case we've got F is equal to, give ourselves a little more space there, F is equal to, our A is 1,000. Now we've got our R is 1 plus 0,18 over 12. So we've got 1 plus 0,18 over 12. That's our R, and we raise it to the power of n. Okay. Then we've got to subtract 1. Now what's often easier here is now we have a second set of square brackets, which I'm actually going to extend. Well, let's just start like that. Then I'm going to extend them down in a moment. And then we divide it by r minus 1. Now r is 1 plus 0,18 over 12, and we subtract 1. So can you see that that actually leaves us with 1,000, 1 plus 0,18 over 12 to the power of n, and actually I realize I made a mistake here, I didn't put n in, so let's just go back here quickly. And we know that our n was 10. Let's pop that in. Okay. 10 minus 1 over 0,18 over 12. And another way to just use your brackets there, which you could have done right from the start, is we could take that 1,000 and just keep it in front and do it like this, where we've got 1 plus 0,18 over 12 to the power of 10 minus 1 over 0,18 over 12. We'll use it like this more with the annuities because it's just a little bit less messy. Now I'm not going to work that out, but if you had to plug that all in your calculator, it would give you the sum of all of these guys, and that would be the sum of all the payments. In other words, to get to his future value. Now, that's okay if we have 10 payments. You see, it's quite time consuming. So we want to eventually get to a formula that can help us. And yes, as you may have guessed, that formula relies on the formula for a geometric series. We don't want to have to plug it in, that formula, every single time. We want a formula that works quick and easily for annuities. So let's generalize this example a little bit. Right, so if we generalize our example, let's have a look at a timeline again. So we're not looking at numbers now. Oopsie, let's try that again. Just extend this guy. Okay. Right, so if we're looking just in general, let's pop in again our T0. Let's put in T1, T2, etc. And if we're generalizing, then our last term is Tn. The one before it would be Tn minus 1, and the one before that would be Tn minus 2, etc. And we're working all the way up to having a future value. Okay, so now we make regular deposits to save, regular saving deposits of X. And then we've got our interest rate I. Now again, let's generalize that. Let's have a look at our future value will be X plus the X before it and all its interest for just one time period, plus the X before that and its interest for 2 time periods, all the way to this X right here, which we know will have n minus 1 time periods. If you look back at the previous example, when it was 10, it had 9 because of our first term. Right, so this first X earns interest for n minus 1. Okay, now let's go again to our geometric series formula and plug in. So let's write down that formula again. We know it is Sn equals A, and actually I'm going to just keep that A out like I did at the end of the previous example, just to make it look a little bit less messy at the end. So we've got r to the n minus 1 over r minus 1. So I've just popped the brackets in a slightly different place. Okay, so that's our sum formula. So let's plug this geometric series into that formula. And in this generalized case, A, our first term is an X. Our common ratio is whatever's in the brackets, which in this case is 1 plus I. And our n, well, that's still just n. So let's plug it into our formula. Remember, we're dealing with future value, so I've got that my future value is equal to A, which is X, open my brackets, and now I've got my R to the power of n, so that's 1 plus I to the power of n minus 1 over R, which is 1 plus I, minus 1. Simplify that denominator, and we get X, open brackets, 1 plus I to the power of n minus 1 over I. And this is your future value annuity formula, which you can use straight away and which we will cover in more depth in future videos. So that's our future value. That's if we want money at the end, in the future. Right, so let's have a little look at what happens if we want a present value annuity. Okay, so our present value annuity, a sum of money is normally borrowed now. That now is very important. It's the money now, present amount of money, from a financial institution and paid back with interest by means of regular payments at equal intervals over a period of time. Or it could be the amount of money that is invested now, so that you can make regular equal withdrawals. The most important thing is that it happens now. You get the money now. Now we could go and calculate the formula for present value in a very similar way using a geometric series that we did for present value. However, it's far quicker now if we recognize that the present value of the annuity is the present value of the amount F, our future value, that has accumulated by the end of the nth period. So we're going from F back to P. Let me show you what I mean. We know that compound interest A equals P 1 plus I to the power of N. We're just not using the letter A now, we're using an F to emphasize future value. So we know that this is true. F equals P 1 plus I to the power of N. Now remember we're aiming for present value, so let's rearrange that by dividing both sides by 1 plus I to the power of N. So would you agree P is equal to F divided by 1 plus I to the power of N. Now that's quite a complex looking fraction, so we know because of the laws of exponents that we can rewrite that as F 1 plus I to the negative N. Now we've just learned our other very handy annuity formula. Just in case you've forgotten it already, let me just pop it on the side here. We know that our future value is equal to X. There we go. 1 plus I to the power of N minus 1 all over I. So we know that. So we can take that guy there and replace this F with that whole expression there. Okay, so let's replace it. So now I've got that P is equal to X, open bracket, 1 plus I to the power of N minus 1 over I. That's my F, and I times it by 1 plus I to the negative N. Now I can take that whole guy there and distribute it to my first term and distribute it to my second term. So I get P is equal to X, open bracket. Now I've got 1 plus I to the N times by 1 plus I to the negative N. The bases are the same, so I add the exponents. N minus N is 0. Anything to the power of 0 is 1. Minus 1 times 1 plus I to the negative N is just 1 plus I to the negative N. My denominator is still I. And there we have a formula for working out present value when we're using present value annuities. So there's our formula.